Today I'm going to start by talking about the basics of diffusion and why we would want to image it. And then I'll move on to generation of diffusion-weighted contrast with magnetic resonance. Then I'll talk about how to design a protocol to meet specific aims. And then at the end we'll talk about some sequence modifications we can make to glean even more information about the tissue microstructure. What I'm not going to talk so much about today is artifact reduction, readout strategies for a diffusion MR sequence, and different ways we can prepare the magnetization before the diffusion encoding block. We're really going to focus on how to do diffusion encoding today. So let's start with the basics. If you put a water molecule into a glass of water, it will move around due to thermal energy, and it will trace a random path. And the probability density function that governs its motion will be, at least away from the walls of the glass, an isotropic Gaussian distribution. So here it is in profile, and here it is in equation form. The variance of this distribution is governed by a scalar parameter called the diffusion coefficient. Now, if we were to put the diffusion coefficient describes the mean squared displacement of the water molecule per unit time. If we were to put our water molecule in some sort of environment where it bumps into things, such as cell walls in tissue, then in this case, the displacement distribution is still isotropic, but the variance will be lower. And we sometimes refer to the diffusion coefficient we would measure in this case as the apparent diffusion coefficient, or ADC. It's lower than the diffusion coefficient of free water, and the discrepancy is given by a parameter called the tortuosity. Now, if we put our water molecule in tissue that has anisotropic structure to it, such as white matter shown here, then I'll just zoom in a bit. The water will diffuse in both the extra-axonal space and the intra-axonal space. And the displacement distribution for it will be anisotropic with a maximum direction along the fiber orientation. So from this, we can infer the fiber orientation. Now, a detailed terminology in diffusion imaging: if we can reasonably approximate this displacement distribution as an anisotropic Gaussian, then we would call it hindered. And if not, we would call it restricted. But there's a very common model in diffusion imaging called the diffusion tensor model that just assumes that on average, this displacement distribution can be described by an anisotropic Gaussian. Here it is. And instead of that scalar diffusion coefficient, we have a diffusion tensor that we'll revisit later in this talk and later today. So why do we want to image diffusion? These are diffusion-weighted images, and just as motivation, I'll show you some of the things we can do with them. We would generally compute maps, such as the mean diffusivity, the degree to which diffusion is anisotropic, the preferred direction of diffusion. And with diffusion imaging, we can also infer more than one preferred direction of diffusion, and from that, infer multiple fiber orientations per voxel. And with these estimates of the fiber orientations, we can compute maps of global connectivity. We can also look at microstructure. This is not a diffusion image. This is a segmented electron micrograph. But with diffusion imaging, we can glean a lot of the information you see in this micrograph, such as the ratio of the extra to intra-axonal water volume, and the average axon diameter, and even distributions of axon diameter. So let's come back to how we generate diffusion-weighted contrast. The first thing we need to do is put our sample in the magnet, and the magnet has a large magnetic field B0 oriented along the z-axis that you see here. And the magnetic moments of the hydrogen atoms on the water will align along that field. So they're all aligned along Z now. To create visible magnetization, what we do is we apply a radio frequency field called B1. So we're going to see that applied here. And then the spins will precess in the XY plane. And the precessional frequency will be proportional to the magnetic field that these spins see. So we're going to look at the same thing now, but we're going to look down on that XY plane. And we haven't excited the magnetization yet, so we don't see anything. And we're going to analyze what happens in this pulse sequence diagram. And we have a couple of tools at our disposal. We have the radio frequency pulses that we just saw excited the magnetization, and we can also create magnetic field gradients, shown in turquoise here, that vary the magnitude of the Z magnetic field. And we're going to use a little trick we often use in MR, which is to go into the frame rotating at the precessional frequencies of spins that see the main magnetic field B0. So what I mean by that is we're going to excite the magnetization. Now we see it in the XY plane, but it's not rotating because we're in the rotating frame. And now we put on a gradient, shown in color here. And so now you're going to see the discrepancy between the precessional frequency of these spins that are at different spatial locations and a spin who just sees B0 in the center. So here we have the spins precessing. So now after the gradient, they have what we call dephased. They're all pointing in different directions. Turn off the gradient, and now they're all precessing at the same frequency. And now we turn on an opposite magnitude gradient pulse. And so now the discrepancy in precessional frequency is opposite. And after that gradient, all the spins have aligned again. So the total signal we measure will be the vector sum of all of these spin magnetic moments. And if we look at a whole bunch of them, we can analyze what happens to the signal. As they dephase, the signal decreases. And now we switch the gradient direction. And now they're going to rephase. So you see that they come back into alignment here. So now what happens, we're going to allow these spins to move or diffuse. So now, during the first gradient, we have signal loss as before as they dephase. We switch the gradient. But now, because the spins have moved, they're not going to see the exact opposite gradient. So what happens is they aren't going to be able to completely refocus. So you get a signal attenuation. And this signal attenuation, because they moved, is what gives us our diffusion-weighted contrast. It's proportional to the magnitude of the motion and the magnitude of the diffusion encoding. So this is the sequence we've been looking at. It's a gradient echo sequence with a bipolar gradient pulse. And we basically never do diffusion imaging like this. I just hope that by looking at it, you learned something. We usually use what's called a spin echo sequence. And what we've done here is we've stuck this 180 pulse in the middle of the sequence. And I'll show you what that does with an animation in a moment. But the 180 effectively reverses all previous gradients. So this sequence is, as far as diffusion is concerned, is equal to this sequence at the bottom. And with the exception of the polarity reversal, it's equal to the top sequence. So let's look at what the 180 does. What we're going to do here is excite the spin, as we did before. And then we're going to apply the 180 RF pulse. And we'll watch what happens. The spin is dephasing, then the 180 puts it exactly where it would have been if it had seen the negative gradient in the first place. Dephase, 180, and now it comes back to the x-axis. So we'll look at our little ensemble of spins who are at different spatial locations again, and just start at the beginning of the gradient. So we see the dephasing, and then we turn off the gradient. And now we're going to do a flip around X as we did before. So just those center spins have flipped, and now nothing happens. And now we apply the same magnitude gradient instead of the reverse. But because we flipped the spins, at the end of this gradient, they're all going to rephase again. So let's look at the whole big population and allow them to move. We have our signal dephasing as we did before. Flip the phase instead of the gradient and allow them to refocus. But again, because we had motion, they didn't see the exact gradient that they saw in the first half, so we have the signal attenuation. So there's one other thing happening during this sequence. Without diffusion encoding, we never would have gotten back to our original signal, because with the 180 pulse in the spin echo sequence, we still have what's called T2 decay of the signal. And without it, we would have had T2 star decay that gets partially refocused by the 180 pulse. So that's happening on top of the diffusion attenuation. So these are examples of diffusion-weighted images. Here, well, the first thing you can see is that the CSF is very dark because it has very high diffusivity. And we've applied diffusion sensitizing gradients in 3 orthogonal directions, shown by the arrows. So in the leftmost brain, you see there are fibers of the corpus callosum that are aligned in a parallel to the diffusion encoding direction, and because diffusion is maximal along those fibers, you see the most signal attenuation there. Likewise, in the center, fibers that are aligned parallel to the diffusion encoding gradient will be the darkest, and at right, it's the fibers of the cortical spinal tract that are going through plane that look the darkest. This is an example of a diffusion-weighted image that in the case of pathology, this was a MCA occlusion, and in the case of infarcts, the diffusion coefficient drops significantly. So we end up with this very bright spot on the right. So stroke is one of many applications of diffusion imaging, and I'm not going to talk about those today. I'm going to come right back to our sequence. But in addition to those diffusion-weighted images, a diffusion study would generally acquire another image with no diffusion sensitizing gradients. So everything else is the same. This is a highly T2-weighted image with the CSF appearing bright. So this is the sequence that we've been looking at. Let's look in a little bit more detail. The duration of the diffusion encoding gradient is usually referred to as little delta, and the time between the onset of the two gradients as big delta. And we can define a quantity called B that's a function of K, which, if you're familiar with MR, is the same K we use in the imaging context, the integral under the gradient waveform. For this sequence, if you perform this integral, it reduces to this quantity here. So B is a function of the gradient magnitude and the timings of the gradients. And this timing parameter at the end is called the diffusion time. This is the effective time over which we are observing the diffusion process. We can also define a quantity called Q, which is also a function of the gradient strength and duration. Q and B are related, but not one-to-one, because Q is not a function of that big delta parameter. So this is called a pulsed gradient spin echo sequence, or sometimes a pulsed field gradient sequence, or a Staggs-Tanner sequence in honor of its inventors. Historical note, the PGSE sequence was invented almost a decade before imaging. So everything we've been talking about can be done without spatial localization and can still give you information about a sample. But most of us here want to do it in the context of imaging. Before the pulsed approach, diffusion encoding could still be done with a constant gradient, but one of the advantages to the pulsed approach is that that diffusion time I pointed out can be very well defined. So here are our diffusion-weighted images. In a diffusion acquisition, we would generally acquire a whole bunch of these. And here I'm just illustrating the gradient encoding directions spaced out isotropically on a hemisphere. And from these many diffusion-weighted images, we could construct, at each voxel, a diffusion-weighted signal profile. So here, I apologize, I don't have a pointer and my mouse isn't working, but here we have a U fiber in the brain, and in the little white box at the left. And you can see that if you look at the center part of the figure, that the diffusion attenuation is highest parallel to the fiber orientations, as we expect. And when you look in the box at the right, in regions where you have multiple fiber orientations per voxel, the signal profile is actually much more complicated. And later today, we'll see a lot more about what we can do with this signal. So we know that we have signal attenuation that is more pronounced when diffusion is higher. But what is the exact form of this relationship? If diffusion is Gaussian, then you will get exponential decay as a function of that B parameter and the magnitude of diffusion, shown here. If the diffusion is an anisotropic Gaussian, then you extend this to the tensor formulation. So I showed you the tensor-based probability distribution. And we invoke something called the B matrix instead of the B value, which allows us to encode the diffusion encoding gradient orientation as well as magnitude. We can also look at the signal as a function of that Q parameter. And it looks a little bit different, but still decreases in the Gaussian case. The signal profile will be Gaussian if diffusion is Gaussian. But for both Q and B, when you go to higher values, if you have restrictions, then it starts to deviate significantly from the shape you expect if diffusion is Gaussian. And here you see that it's not only non-Gaussian, but it's not even monotonic. So maybe later today you'll see more what you can do with this signal of diffusion. So now I'm going to move on to how you could define a protocol to do specific things. So if you just want to estimate the magnitude of diffusion, then at minimum you need a diffusion-weighted image and an image with no diffusion weighting, or B equals 0. And the B value you'd want is generally around 1,000 seconds per millimeter squared. What's really important is the magnitude of the diffusion attenuation. So for example, if you were imaging neonates where the diffusion coefficient is much higher than in adults, you would probably want to reduce your B value significantly. If you want to measure the apparent diffusion coefficient in 3 orthogonal directions, then you would apply diffusion weighting in those 3 orthogonal directions. If you want rotationally invariant estimates of anisotropy and one preferred diffusion orientation, then you would want to image the diffusion tensor. And this is the diffusion tensor shown at the bottom right. It's a 3x3 matrix essentially, and it has 6 unknowns. It's symmetric, and it will have 3 positive eigenvalues. And it's often illustrated graphically with this diffusion ellipsoid. The eigenvector corresponding to the largest eigenvalue will be the preferred orientation, and that's what's shown in the rightmost color plot here. And the variance of the eigenvalues would be the anisotropy, which is shown in the center. Because there are 6 unknowns, we need to acquire at least 6 diffusion-weighted images with distinct gradient orientations. B factor is still around 1,000. But because what's going on in tissue is never a perfect anisotropic Gaussian, what we really want to do with the tensor is find the best fit anisotropic Gaussian. And it's been shown that going up to about 30 gradient orientations is optimal for that. If you want to boost your signal to noise, you can keep acquiring more data, and it's generally advantageous to acquire different data if you do so you could do even more orientations. It's generally recommended to have a ratio of B equals 0 to diffusion-weighted images of about 1 to 10. If you want to infer multiple fiber orientations per voxel, and for most microstructural models, we would generally do what's called high angular resolution diffusion imaging, which by my definition means many more than 6 diffusion encoding directions, more in the 60 to 100 range or more, and going to a higher B value. So the thinking now is that it's good to mix some lower B factor images around 1,000, which will boost your SNR, with the images that have a higher B value that would have low SNR but higher contrast between voxels with different diffusivities. So for example, the Human Connectome project, which is a large-scale study acquiring very high-quality diffusion data sets using over an hour of scanning, has opted for 3 different B shells from 1,000 to 3,000. So that was high angular resolution diffusion imaging in general. There are a lot of specific models in diffusion imaging that you'll see later today. And one of them, NAUDI, allows you to estimate microstructural compartment sizes and orientation dispersion of fibers. And when you look at these models, there's often an optimal acquisition specifically for them. For NAUDI, it comes out to pretty similar to that high angular resolution diffusion scan protocol that I just showed you. There's another model called CHARMED that explicitly models multiple fiber orientations, and its optimal acquisition goes up to almost B equals 10,000, as does the acquisition for something called Excalibur, which allows for estimation of the axon diameter distribution. Here, the diffusion encoding is applied just along one direction, and the fiber orientation is known a priori. So some other acquisition details, you'll generally, for diffusion studies, be around the 2 millimeter isotropic voxel size. But I have seen as low as 600 microns with cutting-edge software and hardware. It's advantageous to accelerate the acquisition through a number of different approaches, including parallel imaging in the slice direction. Simultaneous multi-slice imaging is really revolutionizing what we can do with our diffusion encoding time. It's also good to minimize magnetic susceptibility-induced artifacts that can be quite pronounced in diffusion imaging, and there are a number of readout and ways of doing this that I won't go into today. It's also good to minimize the echo time to maximize signal. So you would want to maximize the gradient capabilities of your scanner. And depending what scanner you have, those are different, but if you're lucky enough to have a connectome scanner, you could go up to 300 millitesla per meter, and that's what was done here. So this is not as achievable with more in the 40 to 80 millitesla range, which is what most of us would have at our disposal. So now I'm going to talk about some ways we can modify our pulsed field gradient sequence. So one thing we can do is we can take that 180 in the middle and we can break it into two 90s. And what that does is it pauses in the middle of the 180 flip. So the first 90 in the center would take the diffusion encoding magnetization and store it along the z-axis. And then you can just wait. And at that time, you wouldn't have the T2 decay. So you can wait much longer than you could if you were limited by T2 decay, and then flip the magnetization back into the XY plane and finish your diffusion encoding. And this is called stimulated echo imaging. And why would you want to do this? Well, you can significantly increase your diffusion time over which you're observing the diffusion process. So a recent example by L. Spearmans looked with long diffusion times at the time dependence of the extra axonal diffusivity. And she was able to go up to diffusion times of 600 milliseconds instead of the more typical 40 milliseconds-ish. So that's STEAM. Now, I've already convinced you that this constant gradient with a 180 in the middle of it can be replaced, as far as diffusion is concerned, with a bipolar pulse. But what you can do is you can take each of those constant diffusion gradient pulses, and with no 180 in the middle of them, and replace them with a bipolar pulse with a 180 in the middle of it. I'll let you go over that a few times as homework, but this is called the twice refocused balanced echo sequence. And why would you want to do this? Well, this can really reduce some artifacts called eddy current induced artifacts that are common in diffusion imaging. What I'm showing you here is a monkey brain that we scanned with a custom coil we built. And these are all the same slice of the same anatomy. But what happens is that the ramp up and ramp down of those big diffusion sensitizing gradients induces eddy currents in the scanner hardware that then induce secondary magnetic fields. And the image reconstruction can't tell the difference between those fields and the imaging gradients. So you end up with image distortions. You get shifts, shears, compression, stretching, and signal loss. And if you time these twice refocused balanced gradients properly, what you can do is pretty much cancel out the eddy currents themselves. So it reduces this distortion significantly. So here is our pulsed field gradient sequence again, and its non-spin echo diffusion equivalent. So I've told you how to increase your diffusion time with STEAM. What if you want to decrease your diffusion time? Well, you can just decrease it, right? And then you're done. But you've already maximized your gradient strength, so doing what I show here at the bottom would significantly compromise your B value. So what you can do is just repeat it over and over again. So now you have a short diffusion time, but a reasonably optimal B value. And I should tell you now that we don't have an infinite slew rate, so really all these gradients are trapezoidal. Through the whole talk, they have been. And so this is an oscillatory gradient waveform, and we'd want to put in a 180 that effectively reverses our previous gradients. And this is called oscillating gradient spin echo imaging. And I'll just show you a recent example. The diffusion time achievable was around 4 milliseconds instead of the more standard 40 milliseconds. And here's an example, again, looking at time dependence of the extra axonal diffusivity, which is the blue here. So I've told you that the pulsed field gradient sequence is sensitive to anisotropy of diffusion. But if you have what's called microscopic anisotropy, or sometimes compartment shape anisotropy, such as shown here at the bottom, this will look isotropic as far as the pulsed field gradient sequence is concerned. So what you can do is add a second diffusion encoding block oriented at an angle that you can control to the first and separated by what's called a mixing time from the first. And this is called the double pulsed field gradient experiment, or double diffusion encoding. And the way I like to visualize what will happen is to look at the limiting example where we just have two different orientations for this compartment shape anisotropy, and they're infinitely restricted. And so now, when you apply your first diffusion gradient, oriented in the vertical direction on the screen, you'll attenuate the signal in those vertical shapes a lot. And if you apply the second gradient in the same orientation, with theta equals 0 there, you won't have that much further you can go before you hit the noise floor. But if you turn the gradient so it's at 90 degrees to the first, then you have all those horizontal shapes with signal that has not been attenuated yet, and you can attenuate the signal much more. So what happens is, depending on the angle between the two encoding blocks, you get a different signal, and it's minimal when they're at 90 degrees to each other. So you get this oscillatory response of the signal as a function of the angle between the encoding blocks. And that allows you to detect the fact that you had compartment shape anisotropy. You don't have to stop at double pulsed field gradients. You can do quadruples. I'll let you study this in your free time, but you can see that there are 4 encoding blocks here. And this was used recently in vivo to look at microscopic anisotropy. The multiple pulse field gradient approach is also advantageous for estimating axon diameters because it makes certain interesting features of the signal as a function of Q or B more pronounced. So a last concept that I want to talk about today is related to the B matrix that we saw in the context of the diffusion tensor. For the single diffusion encoding in the proper reference frame, the B matrix will look like this. It has one non-zero eigenvalue, and you can think of it as a tensor that is a linear tensor. For the double diffusion encoding, the B tensor would be planar. And you can do triple diffusion encoding. Here, if the gradients are applied orthogonally to each other, what you'd get from this is an image where you're weighted to the magnitude of diffusion, but independent of the anisotropy. And the B tensor is spherical. So the logical extension of this is that you can have B tensors of pretty much arbitrary shapes and sizes achieved by gradient waveforms that you see in the left column that deviate significantly from all of the gradient waveforms I've shown you so far today. So let's just conclude that we've just scratched the surface of what we can do with our diffusion encoding. In this framework, which is very recent, called Q-space trajectory imaging, we can look at variations in the size of the tissue microstructure, variations in the anisotropy, variations in the microscopic anisotropy, and variations in the orientational coherence, all by doing fancy diffusion encoding. So I'm going to stop there. My timer wasn't running, so I don't know how long I have. Do I have a minute? I have a minute. I'm going to show you. I'm going to refer you to some nice textbooks on the topic written by experts in the field. And there's a recent feature on the ISMRM blog that I'll just show you for a moment. It extends the analogy Hahn first made of the spin echo using runners on a track to look at diffusion. So this is our track. We've linearized it, and we've turned our runners into little blue dots. And we're going to watch them run, but we're going to imagine that they're slightly inebriated. And so they're going to be switching lanes. So here, signal attenuation is proportional to the total variance of the dot position relative to that red line. And then we have the magic 180, and then refocusing. But they won't perfectly refocus because they've moved lanes. So what you can do on this little applet is you can play around with your B factor, which is a function of the gradient strength and timing, and your magnitude of diffusion, and you can see how the signal attenuation depends on both of these. So I'll leave you with that, and happy continuation of your diffusion education.